Hi, thanks. Shawn Oram with Ecotope. Again, thanks for having me. It's a pleasure talking to you about some of the stuff we've been working on, mostly focused on central heat pump water heaters for large commercial buildings, mostly apartment buildings.
Next slide.
Next slide. Sorry, what was it? I think you did, but okay, got it.
No.
Oh, that's it. Okay, I missed the cursor. Thank you. All right, so here's a quick agenda for today. I'm going to discuss kind of high-level central heat pump water heating. I'm going to talk about some of the best practices in design and commissioning. Talk about some of the current issues. Talk about the market development, kind of where we see things, and maybe some next steps. Quick overview of Ecotope. As Shawn mentioned, we are a firm focused on efficiency. We've been around since '76. Worked with some of you guys, some of the former founders. I've worked with a lot of you folks here. But we basically have three divisions: engineering, design, research, technology, policy, and planning. Together, all three of those are focused on sort of moving buildings to carbon neutrality. So central heat pump water heating, we've been at central heat pump water heating since 2008. We've done about 20 systems. We've learned a lot of things in the process. Hopefully today I can kind of share some of that with you. Most of our projects have been on buildings in the 100 to 500 unit build type of design. Quick overview.
Next, so you're on.
Oh, I'm sorry. Yes. So next, central heat pump water heating. Next. Yes.
Multifamily energy and
Good point. They weren't done. That's a good point. Yes, it always looks better. Yeah. Okay, so this represents an end use of energy use that we've found in Seattle buildings. These were all built to 2010 code, and we took 10 about 70 to 200 unit, what we call built smart. It's a utility program. So these are more or less code compliant buildings, and this is where the energy end use ended up being. And if we look at this total pie, this is an EUI of 40. So this is kind of where we start the game on multifamily construction. And if you look at kind of the breakouts, you can see quarterly there's unit non-heat. These would be plugs and appliances, lights. Common non-heat would be elevators, lights mostly, and then random plugs. Unit space heat, common space heat, about 5 EUI points. So these are kBTUs per square foot. And then the green is what we're going to focus on today. That's the heat. That's the central hot water heating system. And a further breakdown is about 3.5 EUI, or about 35% are associated with the actual what we call temperature maintenance, which is keeping the pipe hot. So that's a third of your energy, is just maintaining the loop. The other 2/3 are the actual physical heating of the water. And before we started down this path, trying to understand this, we had no idea what this temperature maintenance piece was. And everyone else thinks it's a 15, 20% problem. No, it's way bigger. And I've seen this be equal to the hot water load. It's purely a function of insulation. That is all this is. It's not starting a pump. It's not stopping it. It is purely pipe UA. That's all this is. What is the game as designers? We have to reduce the UA. U value, which would be your insulation times your area. That is the whole function here. And you can't just focus on the plant without also focusing on the distribution. Hopefully today I'll kind of cover the most important pieces of this. Next slide. So big picture heat pump water heating. We all know what heat pumps are. I'm going to assume we all know what heat pumps are. They move heat. We've got a refrigeration cycle between two sources, an outdoor source and in this case a water source. The point of this slide is showing that stratified storage is hugely important. It's important for the function of the heat pump. It's also important for just delivery of hot water. Next slide. First, we can't skip over this because this is a hot topic, kind of aligns with a lot of the methane leakage stuff, but the GWP of various refrigerants. This here is a stacking of kind of the best and worst. Obviously, the higher up this chart or the lower GWP is kind of where things need to go. Most of the equipment now is focused on the traditional 410A and the 134A stuff. You can see their respective GWPs. We're starting to get a lot more into some of the CO2 stuff with the stand-ins, trying to push the industry to bring more of this product in, because I think the CO2 stuff is kind of where things should land. But we should definitely get practice on this other stuff, because it's one thing to have a CO2 heat pump, but if you don't know how to design it, and we have definitely learned our lesson. So I'm happy to share more of that. Another really interesting piece that, the next slide, thank you, Shawn. Another really important piece here coming is this magnetocaloric heat pump technology. GE and Oak Ridge have been kind of quietly busy preparing a refrigerator which has no refrigerant. Now, if this can be taken to scale, this whole refrigerant GWP thing is, that's yesterday's story. So something to keep an eye on. I think this is really, really exciting.
Just like the same thing with induction.
No, it's different. No, look YouTube this if you're curious. Magnetocaloric heat pump. It's actually being developed now. 2020 is when GE will have this product. So keep an eye on this. Right now it's small scale, but it can do. It's magic. It's basically applying a current to a magnet creates heat. And so it's this principle here. But if you go online, I could spend a lot of time talking about this. Yeah, but check it out on YouTube. There's some pretty good videos, and you should understand it. But it's fascinating. So just keep an eye on it. Yep, it's a standard refrigeration cycle, and you just have to kind of optimize how it's set up. It's obviously got to be developed for a particular purpose. In this case, it's just a standard residential refrigerator.
What kind of COP could you get with it?
This thing is claiming 20 to 30% higher COP or efficiency over a refrigerant-based system. So if we're running COP3s on refrigerators, higher math, 3.5, 4. So pretty remarkable if this,
Your refrigerator is your what?
No, not in this case, but there's not enough energy. The scales are the magnitudes are much different. Next slide. So kind of jumping into best practices in design and commissioning of these systems. I've kind of broken this down into about 8 different steps, and I'll highlight these on the next slides. Again, we have done about 20 of these, both big and small. We've had a lot of failures, and we've learned from them. And I'll hopefully try to tell you some of the things that we've learned, and definitely ask questions. So first piece of this entire equation are, you've got a big multifamily building. Where do you start? And next slide, thank you. So step 1 is really understanding the load. And right now in a multifamily building, there's really 2 loads. There's the primary hot water load, and there's what we call the temperature maintenance load. This is keeping the water hot in the pipes. Those are 2 loads. You have to respect them, because if you don't, they will mess things up. And I'll tell you some examples of how. But usually the temperature maintenance load, it's a really hard thing to calculate. The only way that we've been able to find it is to actually measure it. So we set up BTU meters on a RECIRC loop, and we measure this thing through many years. And that's how we've discovered it. And we've got some metrics. So I can look at a building and say, that's about 70 watts an apartment. That's the metric I use. The range is 50 to 400 watts an apartment. So if you take your number of units times a range of 50 to 400, purely a function of insulation levels on your piping, how you're clamping these, how you're insulating. Remember, this is an entire hot loop. It wants to lose heat. They're trying to contain it. That's the key piece. But that's the load on the temperature maintenance. It ends up being about, like we showed earlier, about 1/3 of the total hot water load, just priming that system. We can't ignore that if we're going to be pushing hot water systems to low EUIs. So the next piece would be identify the heat source. There's several options, but outside air, that's kind of the easiest. A buffered space, below grade parking garage. This is where we've had the most success. So on big 5/1, 5/2 apartments, we put the heat pumps in the garage. We never see lower than 50 degrees in a garage. Keep in mind in Seattle, design temp's 23. And I'll show you some data from that, but essentially they stay at ground temperature. And so they'll follow the water temperature. Once you're below ground, below about 10 feet, it stabilizes. So we can run these heat pumps year round at pretty good COPs and they act kind of like a garage exhaust system. So that was kind of how this started. We said, hey, we're throwing all this heat out. Let's try to capture it. Another piece, a system we've tried is to put the heat pump inside of a solar greenhouse. You get another half to a full COP if you do that, but be careful, the greenhouses get really hot. Some equipment don't like it too hot. Stand-ins start to have problems above 110. Just keep that in mind. Ground source is another obvious one. That's a big cost, but we've done a few of those. And then wastewater source is not to be overlooked. So in an apartment building, all of your wastewater comes down. We've got a project in Seattle. It's 300 units. We're collecting all of the wastewater. We've got heat exchangers in the bottom, and we're extracting out. The projection is COP4, so we'll see. We started up next month, so pretty excited.
Shark was going to be here, Lynn of Shark.
Yeah.
This is the wastewater heat pump company, a family issue, so you couldn't leave Canada and get here, but I just want to validate that's a real thing.
Oh yeah, no, it's huge, and with our air source systems, COP3 is pretty easy to get to. If you want to get beyond that, you need to be looking at wastewater source. It's a lot of messing around, but
Wastewater can be pretty close. I mean, how do you keep the system from just ending up mixing the two?
yeah, no, that's a good point. We've actually built a vault that's 20 by 20 by 30 high. It's in a parking garage, kind of partitioned it out, and we've got Ben on our team has designed this tree, and so this temperature tree, so we can look at the stratification inside of there. So we'll have a lot of data from this, but it's all kind of a bit bleeding edge. So I don't really have the answer yet for that, but we'll kind of see how things work.
Next retreat.
Next retreat, yes. Lynn's done quite a bit on this. He kind of gave us the idea. We didn't use his system. We did something a little different, and there's a couple reasons why, and I could offline touch on that. Okay. Yes, we got it past the plumbing inspector. It was difficult.
But maybe you're not putting potable water through.
Absolutely not. No, right. It's a totally separate double wall heat exchange between the heat pump and the source. It's basically like a ground source heat pump, except minus the ground bores. We're just putting a heat exchanger inside of a big bath of all of the building's wastewater. What's that? Close loop, yeah. Anyway. Yeah. Next slide. So the next piece would be to select your heat pump technology. There's 4 or 5, maybe 6 players out there. We've all had some experience with it. I don't want to go through these, specifically, but each one kind of has their sweet spot, and it really comes down to 2 things: what the refrigerant is, what the compressor is. It's either a variable or a fixed. Those 2 alone will determine sort of what heat pump you should be using. I've got these 2 items over to the right, which are green. Those are the CO2 heat pumps that we need to bring into this country, but we cannot get them. This is where we need help. We need help as an industry, support, funding to get this technology. It's for sale on the other side of the world. We just need to get it in here and use it. But this is really exciting stuff. So and I'll touch on that too. Exactly. Okay, next. The next piece in kind of this approach would be to understand your design, or to kind of hone in on a design. And there's 2 ways to heat hot water in the technology that's out there now. It's either a single pass or a multi-pass. A single pass device will take 50-degree water and heat it up to usable 140 degree, a single pass. A multi-pass is more like a boiler indirected. So you'll heat 10 degrees on each pass and bring the whole thing up. This is really important, understanding the difference here, because the implications are, when you do single pass, you can bring 50-degree water into your heat pump. That is a sweet spot for heat pumps. So the game here is to set your heat pumps up in a single pass so that you're always bringing in the coldest water possible. That is your efficiency gain. Next is choose how you're going to reheat the RECIRC system. There's 2 ways to do it. You either have a primary hot water storage and you run your RECIRC through that. You have 1 heat pump or stages of them that manage that. Or you simply split off the function. You've got 1 heat pump system that does just the water heating, and you've got a separate one that just does the temperature maintenance. our best designs, our most efficient designs, our most sort of, you know, less troublesome designs are where we split them off. And that's kind of what we've been honing on is temperature maintenance is one heat plant, and primary water heating is another. They both shine when you do that. That's an area that we've been focused on. Thanks. 10-minute layout. Okay, next slide. Choose location and layout. So obviously the layout's important. This is kind of standard design. Just make sure you can get your gear in and out. Next piece would be your storage design for stratification. So stratification is very key. Yes, go back.
From Zoom.
Yeah.
Single pass versus multi-pass. What is the efficiency difference one can expect? Is there an efficiency difference to note?
I would say it's probably, I can show it to you, but about 0.7 COP, and I'll show you some. I've got some M&V data on one particular case study, which will be at the end, and I'll show you the difference.
Greater or less?
Greater efficiency by 0.7 COP using weather data now. So I've got data.
Single pass.
Yes.
Single pass being more efficient.
Yes, because of the colder entering water, and that's the difference. Is the cold water coming in makes the heat pumps shine. Yep.
Can you talk about like pairing with solar thermal and that temperature difference degradation?
Yeah, that's an interesting conversation. And the way that I would deal with solar thermal, I think on a big central system, as opposed to doing a preheat, I would set it up as a stage 1, regulate the flow, take it up to your collectors and say, here's stage 1, let's slow it down and make it a single pass machine. When that's not available, go to the heat pumps. That's how I would deal with it.
It's in our standards now.
Right.
Some of our plants require 35%.
But you could, if you could do that as your primary plant and do it as a single pass, then you don't degrade the water going in on the heat pump side.
Question, have you ever tried a system where you had a large tank where it brings in outside water and then it passively has it go up a few degrees just sitting there from ambient?
Oh, just to capture any of the gains?
I mean, just the difference between, let's say, 50-degree incoming water versus 65, 70-degree temperature in your garage or something like that.
Oh, yeah, I mean, it's not a big number, but I think that's, yeah, I guess we haven't actually tried to try and, yeah, that's an example.
That's more accurate.
Yeah. Yeah, I guess we haven't really tried to have a preheat where it's just absorbing ambient in a space. I mean, it's similar to that, but it's just, yeah, I mean, this is kind of focused on the plant. All right, so time is I want to get to the M&V stuff. So let's see, I'm on storage design for stratification. So again, stratification is really important. You want to make sure you set these systems up. You know, don't use horizontal tanks. You know, too small a storage is a problem because then when you have peak flows, you end up mixing the whole tanks. So add some storage. Poorly insulated tanks, they lead to degradation of the hot water tank. So what you got to make sure that your tanks are well insulated. Here's again, the segue into super-insulated tanks. So we've got our 17 500-gallon tanks here. These are pretty common that we use, and then we wrap them with another 12 or 13. So we try to hit R25 on our storage tanks. These ones are, I think, RBI. There's a couple.
Multiple tanks, or are you piping them series or parallel?
Series. And that's, you know, multiple tanks in series is the same thing as one giant tank, like this. So your efficiency is way higher because all this is hot. Whereas if you do parallel, then you always have that cold in the bottom. So you need more storage.
What we're saying on the left side of that picture, giant heat gap.
Yeah. So what we saw in these buildings, and I'll cover some more of this, are you got this big thing of hot water in the basement, and the water just wants to climb up your cold line. So we put this 5-foot heat trap in to stop that from happening. But again, we wouldn't have known this without the extensive M&V that we've been doing. Bonneville Power sponsored a lot of our M&V efforts. So that's a huge piece of this. But just having that extra, you know, funds to kind of take care of answering the riddle, per se. Next slide. Distribution. So again, distribution is purely a function of piping surface area and insulation. Here's some of the things we do. So right sizing all of your piping is really important. Optimize the distribution design for the lowest surface areas, and then back-to-back plumbing stacks. Also, we've switched our spec with the new UPC to 3/8" runouts. So come up into a unit, hit a manifold, hit all 3/8" lines, and feed all your fixtures that way. The wait time is way less. So you can cover all of your wait time allowance from one area, but and also the heat loss is less. But 3/8 piping does work in multifamily. Okay, I've got 5 minutes to go. Here's an example of back-to-back stacks. So that's a great idea. It reduces your stacks by 1. Send one up for 2 areas and hit both sides. Next slide, controls design. Most of our larger systems, we use a DDC. This is part of the issue with the industry is they're not set up. No one's set up, nor do they understand this problem of what we're asking of them as designers. So we've just had to do our own controls. Diagnostics are really key. So once getting sensors, getting M&V systems in are very crucial to making sure that you're going to be successful here, and also understand how to troubleshoot. That's a big piece. Commissioning is hugely important. Make sure we've got several clients that are. Oh, sorry. Next slide. Commissioning. Make sure your backup systems work, because when you start into this arena of heat pump water heaters, you will have failures. A lot of them. We've had them. We don't have them anymore, but we used to. But making sure those backup systems working is very crucial. And then M&V equipment. We've had a lot of power quality issues in Seattle. It's something that's unheard of, but there's 65 cranes in the air, and so everyone's disconnecting from the main and connects up, and so we get this little hiccup, and some of the equipment's really sensitive. Colmac gear can be, so that's one thing we've discovered. You can also, the other thing to watch M&V for is you can see refrigerant loss. And if you see a degradation in your COP, you're losing a refrigerant. So you need to go charge it up. And then we've got alarm systems built into all of our controls. So anytime anything goes wrong, we get an email, unfortunately. But that's the nature of the beast. Next, so I wanted to kind of close out. I have 3 minutes on this case study. This is a project we just wrapped up. I'm on case study RCC. So RCC is a term we coined. It's reverse cycle chiller. This is really putting a heat pump into a parking garage. That's RCC system. So now all the architects say, hey, you want an RCC? Yes. So that's one thing we're kind of proud of. So here's a 194 unit. This is an all electric building. The EUI on this building is projected at 18. So this is almost 60% reduction. It's all electric fireplaces, which are pretty remarkable. Heat pumps, lots of heat pumps in space, lots of ductless splits, and then the hot water system is the RCC. So here is next. I'm in the mechanical room. We can see kind of a typical layout. We've got tanks over to the left. We've got two 11-ton heat pumps. This is 194 units. 2 11-ton Colmacs. And these are taking air from this grill below. So what we do is we force the air into the parking garage. It goes down the ramp, go to the bottom level, come up through a floor grill, and then out. And that becomes our exhaust room. So we've got our heat plant in our parking garage exhaust room. The temperature never drops below 52 in this garage. So that's kind of how this does. And then we're allowed, then part of the sale is, look, we don't need such a big garage exhaust system. We've got it covered here. So we can kind of show, there's some savings there. But again, looking at this, you can see our red meter M&V piping mounts are, there's no thermal bridging in there. These are 2-inch insulation wrapped. So this is kind of indicative of what we've been doing for what I would quote unquote RCC system. Here's another angle, kind of see some more space. I realize I have 1 minute. What we've been doing in our designs, we've got dedicated heat pumps for the primary water heating and dedicated for the ring main, or what we call the temperature maintenance. We bring them together into a motorized sort of automated mixing valve by Powers. It's a great valve to use. It can take any variation and deliver your output water. Okay, so here's the fun stuff. So this is the M&V optimization. Next slide, and this is some actual data from what we have been finding. And so we've got an M&V system. It tracks 5-minute data. We're downloading once a day, and so we can monitor this thing. If you look at kind of the progress, this is about so we started the building up in February. We had some issues. April, we were kind of online. We made a controls change May 1st. We made the final controls change June 1st. So we went through 3 iterations on this design and finally arrived. If you look at the middle graph, you can see the COP. The purple line is the temperature maintenance. That COP is running about 2.5. That heat pump runs pretty much consistently year round. That's always maintaining the loop. And then these little stabs down at the bottom show our cycles of heat pump. We're running the heat pump once every 12 hours. And we charge up this whole storage tank, run it down, and then charge it up. The big controls change, we're backing off of being really conservative. We just said, go to the middle of the tank, set it to 90. When this buffer of cold comes in, we hit that 90 degrees and then we run it. And we're trying to run it and push the plunger back to the beginning. Maybe that's a little bit overheads, but that's really what happened is by having this data, we're able to just go in, dial in, make a change, and then go look at it. That is hugely important. Yes, yeah. Commissioning, right. Well, I mean, we thought we had it right with the controls at the beginning. We were firing too much resistance. And so that's what this gold bar is. But we got rid of all the resistance. And if you look at the COP graph, you can see we're running about a 3.3 COP on our heat pumps, on our main hot water plant, and about 2.5 on the RECIRC. Here's the next slide. I know I'm over, but if you look at the air temp above, you can see the air temp, which is GAT, garage air temp. It's quite a bit higher. You know, it stays around 50, 60, and you can see the NOAA weather station data kind of drifting up and down. But basically, this is showing how, you know, the thermal advantage of locating below grade. Again, there's more stuff down below. One thing I'll point out in the water temp graph down at the bottom, this is the entering water into the heat pumps. And so if you look at kind of the COP above, you can see that we've kept this entering water below about 80 with the new control setup that we've got going. And then that directly correlates to COP. So that's a huge piece there. It's just making sure you're entering water into your heat pump. It's always, you know, below 90 is a good target. And then you get that with single pass design. This is zooming in for a 2-day stretch. Next slide. So next slide kind of shows the input power, which is the third graph down, the blue. It shows we run at about 11 o'clock till 2 in the afternoon. So we did all our morning rush, and then there's another call, you know, and these are random, but we can control these. When you put big enough storage in, we can control when we want to fire this heat pump. So this is really, you know, what we're working on next is integrating demand response into this. Keep in mind, in Seattle, we're a bit spoiled. Our energy is 8.5 to 9 cents always. We don't have time of use issues. You know, we're 90% hydro, and so that's the deal there. So yep.
Distribution system or for the main heating?
It's for just the heat pumps. So it's just the primary plant. Right now, we just turn 2 heat pumps on, run it for about 4 hours. We heat up 2,500 gallons of storage, wait for the next call. We let our storage drift down to about 90 in the middle, fire it, and then heat it back up. We can do that. We can control when we fire based on what that set point is. We can also have a little control over, you know, additional firings. So
We should wrap up.
Okay. Yeah. Yeah.
Back up to 128.
We're always running that system, the distribution. Okay, I have to wrap up. So here's the end game with central heat pumps, I guess in my opinion. So low GWP refrigerant, it's very key. You know, variable and fixed capacity heat pumps, air source, you know, plug and play design, making sure you've got redundancy built in. All of the systems we've been doing have backup electric boilers on them. We've had to rely on them when things go south, but so far we haven't had problems on this one I told you. Obviously the high performance hot water distribution design, M&V systems are really crucial in this kind of early stage. And then making sure that they're demand response capable. I think that's kind of where things should be heading. My time is up, but I've talked about market development needs, and I guess I would summarize that I don't think this industry is anywhere near being able to kind of launch full-scale heat pumps yet. There's too much, there's not enough information both at the manufacturer level designers are starting to just get into this and starting to understand this problem. But the momentum behind the fossil fuel industry and getting boilers and tankless and everything, I mean, we need that to happen for these heat pumps, and that's really what's got to happen. We need support from design, from tests, from Title 24, the whole deal. But we're seeing other people kind of approach this. We've got a little bit of a head start because we started 10 years ago, and we're seeing the same mistakes being made. So definitely some consensus and some organization around that would be key.
That.